Hello, welcome to the third podcast of Math-S400, Mathematics and Economic Modeling. In this third lecture, we're going to talk about sequences of real numbers, and when these sequences converge, you will also see some useful properties of convergent sequences in two theorems that we're going to prove. Okay, so let's start by going to the whiteboard. So first we need to define a sequence, and we're going to talk about sequences of real numbers, so sequences in R. Later on in the lecture, in one of the following lectures, we will talk about sequences of vectors, but now we're mainly going to focus on sequences of numbers. So what's a sequence in R? Well, simply it's a list of numbers. So for example, 3, 2.5, 7, I don't know, it can be negative numbers like minus pi, for example, and so on and so on. Okay, so what's the idea? The idea is that this is a sequence of numbers, but it never finishes, right? So this goes infinitely long. Okay, so a sequence is infinite. So how can you define this thing in a mathematical way? So one thing that you could do is the following, right? So first you write down all the numbers in natural numbers that you can think of. For example, 1, 2, 3, 4, and so on and so on. Okay, so this list goes infinitely long because you know there's no biggest number in N. And then for every number you can associate a number in R. Okay, so for example here the first number is 3, then the second number is 2.5, the third number is 7, the fourth number is minus pi, and so on and so on. Okay, so in this respect you have a mapping, right? So the first number is 3, the second number is 2.5, the third number is 7, the fourth number is minus pi, and so on and so on. Okay, so for every number in N you have a number associated in R. So this is called the first element of the sequence, right? Because it's associated with number 1. This is the second element in the sequence because it's associated with number 2. The third because it's associated with number 4. The fourth number, and so on and so on. Okay, so looking at it from this angle, what you have is you have a function that takes a number in N and outputs a number in R. Okay, so you can say a sequence is a function, okay, let's call it f, that takes a number in N and produces a number in R. Okay, and then you can say f of k, let k be a natural number, then f of k is the kth number in the sequence. Okay, so this could be used as the formal definition of a sequence. Okay, it's simply a function from N to R. In practice, we never use this kind of notation to denote a sequence. So what we normally do is we say we have a sequence exists of a list of numbers, and then we call the first number, say, x1, we call the second number x2, the third number x3, the fourth number x4, and so on and so on. Okay, so if you use this kind of notation, then the first number maps to x1, the second number to x2, the third number to x3, and so on and so on. Okay, so here x1 is 3 for this sequence, x2 is 2.5, x3 is 7, x4 is minus pi, and so on. So the advantage is that you, by using the sub-index to denote what kind of which position the number has into the sequence, you immediately see which element of the sequence you refer to. Okay, so that's what we're going to do, and instead of using f to denote the sequence, we're going to denote the sequence by xi. We're going to put it between brackets, and then we say that I ranges over all natural numbers. Okay, so this is an abbreviation of this very long thing that you, in practice, you cannot write it down, but we write it like this. Okay, so we're going to denote sequences as this, okay? And then here xi is a ith element in the sequence. Okay. So this is in terms of notation. Okay, so a sequence, an important thing is that it's infinite, right? So it never stops. We're talking about infinite sequences. You can represent it by function, but in practice what we will do is we're going to denote sequences by this thing. Okay, so this notation captures the entire infinite sequence that we want to talk about. Okay. So an important notion of the sequence is what we call convergence. Okay. So what do we mean by a sequence to converge to something? Well, intuitively it means that if you take the sequence here, then these numbers get closer and closer to some particular number. Okay. And now it's a bit tricky to define what we mean by closeness. Let me take a new sheet of paper. Okay, so convergence. So I'm going to write down the definition, and then I'm going to try to explain to you what this definition means. Okay. So the definition is the following. It uses quantifiers, several quantifiers in fact. So it says that for all epsilon, and epsilon is a number that's strictly positive, there exists a number, let's call it big N, and here because there exists S after the epsilon, this big N can depend on epsilon, right? So for every epsilon you can take a different N. So what we can do is we can put a subscript epsilon below the N. This is just to indicate that this N can vary over epsilon, right? So for different epsilons you can take different big N's. Okay, so this big N has to be a natural number. And then we have that for all, let's call it small n, greater or equal to this big N. And then we have an expression. Okay, so we have three quantifiers here. And the expression is the following, that the absolute value between xn, the absolute value of xn is smaller than epsilon. Okay, so this is a definition of convergence, and in particular we say that the sequence of numbers here, going to call it xn, you can call it xi or xn, it doesn't matter, right, because it's an index. The sequence xn converges to 0 if and only if, well, it's a definition, right, if this condition is satisfied. Okay, so let me read it out loud. We have that for every epsilon there exists a big N, such that for any numbers greater than this big N, xn, which is here the nth element in the sequence, is smaller than epsilon. So let me try to give a graphical illustration of this definition. Okay, so here we have the real number line. Here can be the number 0, and then what we have a sequence of numbers, right? So for example, x1 is here, and then x2 might be here, then x3 might be here, x4 might be here, I don't know, x5 might be here, and so on. Okay, so the sequence of numbers, these are just numbers on this line. Okay, you can plot all of them. Of course, you need to plot infinitely many of them, but in principle, this is how it looks like. So what do we start with? We start with the notion that for any epsilon bigger than 0, something has to be satisfied. Okay, so let us take an epsilon. Okay, so let's picture this epsilon on the graph. In particular, let this be epsilon, and then if you have epsilon, you can also plot minus epsilon. Okay, so important here is that epsilon is strictly positive, right? So it cannot coincide with 0. It has to be on the right of 0, and then minus epsilon has to be on the left of the 0. Okay, so for this particular epsilon, this definition says that we can find a big N such that for any and after big N, the nth term has to be smaller than epsilon, the absolute value. So what does it mean for the absolute value of xn to be smaller than 0? Well, it means that xn is in this interval, right? The interval, it doesn't exclude minus epsilon and epsilon, but xn is somewhere here in this open interval between epsilon and minus epsilon. Okay, this definition is the same as saying that minus epsilon is smaller than xn is smaller than epsilon. Okay, or xn is in the open interval minus epsilon, epsilon. These are all equivalent definitions of this here. So what do we have? We have an epsilon. Then for this epsilon, we can find the big N such that for any term further on, it is in this interval. Okay, so in particular, we need to find the big N. Okay, such that if I look at xn epsilon, it should be in this interval. And also xn plus 1, epsilon plus 1, should also be in this interval. And then the other element, xn plus 2, should also be in this interval. Xn plus 4 should also be in this interval, and so on and so on. Okay, so whatever I have a sequence x1, well, let me write the sequence like I did before, right? So we have the sequence x1, x2, x3, and so on. Suddenly we hit x and epsilon. Then we have xn epsilon plus 1, xn epsilon plus 2, and so on. So I can find the big N, right? I can find some big N in this sequence, such that if I look to the right here, everything is in the interval minus epsilon, epsilon. Okay, so this is what this definition means. So far I have just chosen one particular epsilon, right? But this definition says that it has to hold for every epsilon. Okay, so no matter small, I can take this epsilon, right? So no matter small, I can take this interval around 0. It's still possible for me to find a big N. So some part in the sequence, such that if I go beyond this part in the sequence, I will always be in this interval. Okay. So in some sense, you can say if the sequence goes far enough, you will get arbitrarily close to 0. This is the idea of convergence. Okay. Okay, so this is the definition of convergence of a sequence xn. This sequence converges to 0 if this definition is satisfied. So let me give an example of how this definition may work. So consider the sequence that starts with 1, and then the second element is 1/2. Third element is, 1/3. Then you have 1/4, and so on and so on. Okay, so in general, the nth element will be 1/n, or we can write this as being the sequence where xn is equal to 1/n. So I hope you see that if n gets bigger and bigger, this number gets closer and closer to 0. Okay, so you would say, okay, I suppose that this sequence converges to the number 0. So let's show that for this sequence, indeed, this condition is satisfied. Okay, so what do we need to do? For every epsilon, we need to find a number big N that satisfies this definition, in the sense that for every number greater than this big N, xn is smaller than epsilon. Okay, so let's fix an arbitrary epsilon bigger than 0. Okay, now we need to find a big N that satisfies this definition. Okay, so one thing you can do is you can say, okay, I choose this big N, and then you have to show that it satisfies the condition. Otherwise you can, but the problem here is that you don't know what this magical big N is going to be. Okay, so first we need to do some searching. Once we have finished the searching, we know what the big N is, and then we can state, obviously, okay, here's the big N, and I have proven that it satisfies this definition. So let's first, on a sketch piece of paper, let's first try to see what this big N might be. Okay, so what's the idea? The idea is that we need a big N such that for any N greater or equal to this big N, xn is smaller than this epsilon that we have chosen here. Okay, so what's big N? Well, we know what's xn. Well, we know that xn is 1 over n. Okay, so we have the absolute value of 1 over n has to be smaller than epsilon. Absolute value of 1 over n, simply 1 over n, and you know that this has to be smaller than epsilon. So if you bring n to the other side, you know that epsilon is strictly positive, so we can bring it in the denominator here. So we have that 1 over epsilon is smaller than small n. Okay, so we need to find the big N here, such that for every small n greater or equal to the big N, n is smaller than 1 over epsilon. So what can we do? For example, we can take n epsilon to be the smallest number in n larger than 1 over epsilon. Okay, sometimes in mathematics you write this as 1 over epsilon, and then with it's not the absolute value, but this is called the smallest number smallest number, natural number above 1 over epsilon. Okay, so it's the floor function if you know something about programming of discrete mathematics. Okay, so what do we have? If you take n to be this number that's bigger than 1 over epsilon, well, then we have that if n is bigger than n over epsilon, small n will also be bigger than 1 over epsilon. Okay, good. What you can also do, you can take n epsilon to be the smallest number than 2 over epsilon, right? You can take 3 over epsilon, you can even take 1 over epsilon plus 100, whatever, as long as it's strictly bigger than 1 over epsilon, we are happy. Okay, we don't really care. The only requirement is that n epsilon is larger, is a number, but it's larger than 1 over epsilon. Okay, so now we have here, we fix an arbitrary number. Now we need to know what big N has to be. So take an epsilon, which may depend on epsilon, larger than 1 over epsilon. Okay, for example, smallest number above 2 over epsilon. I don't care, as long as it's bigger than 1 over epsilon. So we assume that we have found the n epsilon. We still have to show that for every small n bigger than n over epsilon, this is true. So if n greater than n over epsilon, what do we have? Well, we have that the absolute value of xn is equal to 1 over n. N is bigger than n epsilon, so we know that 1 over n is smaller than 1 over n epsilon, right? And because n epsilon is larger than 1 over epsilon, I know that this is smaller than epsilon, so we have shown indeed that xn is smaller than epsilon. Okay, so this is, you can say, is a formal proof. This is a scrap piece of paper in order to find out what the value of big N epsilon could be. Okay, so we have taken an arbitrary epsilon. We have found an n epsilon that satisfies this part of the definition. And because epsilon is arbitrary, we can do this for every epsilon, so it actually holds for all epsilon strictly bigger than 0. Okay, so notice that the strict positivity of epsilon is important, because otherwise you cannot bring this to the other side. Then you have 1 over infinity, which is not well defined. Okay, so this is an example of how you can use this definition to verify whether a sequence converges to 0. So we have seen that the sequence xn and r converges to 0 if this definition is satisfied. So for any epsilon strictly positive, there exists a big N that may depend on epsilon, such that for all small n bigger than this big N, xn is smaller than epsilon. So in many cases, we're not really interested in convergence towards 0, but maybe we want to see if a sequence converges to what we call another number, different from 0. Okay, so we can say that xn n converges to, let's say, x in R. So what we're going to do is we're going to mimic this definition, and we're going to change one small part. So we're going to copy for all epsilon bigger than 0. There exists a big N epsilon n, such that for all small n greater than this big N. And now we're not going to look at the absolute value of xn, but we're going to look at the absolute value of xn minus x. Okay. So this is quite similar to the previous step. So if we have the line R here and you have X here, then you can make the same picture, right? Because here this definition will be satisfied. This condition is the same as the condition that X minus epsilon is smaller than Xn is smaller than X plus epsilon. Okay, so in other words, Xn is in the open interval X minus epsilon, X plus epsilon. Okay, so I can add an amount epsilon above X, an amount of epsilon below X, so I get X plus epsilon and X minus epsilon. So if I find my picture again, so here we had an interval of epsilon above and epsilon below with respect to 0. Here we have the same thing, but now with respect to x, right? So this definition says that for any epsilon, right, we can draw an interval, and then I have to find the big N, such that for any element in the sequence beyond this big N element, they're all in this open interval. Okay, so x and epsilon might be here, and then every element in the sequence beyond big N element will also be in this interval. Okay, so the definition is quite similar, right? So instead of, in fact, this definition that xn converges to x is the same as saying that the sequence xn minus x, right, converges to 0. Okay, because if you look at the sequence where the nth element is xn minus x, right, so we can then say, okay, this is the sequence, let's say yn is equal to xn minus x, then this sequence yn will converge to 0 if this sequence converges to x. Okay, so in principle you can define convergence towards a number as converges towards 0 of another sequence. Okay, so writing down xn converges to 0, xn converges to x, this is often quite time consuming, so we're going to use a shortcut in terms of notation. So if a sequence xn converges to 0, we will often write xn and then we have an arrow to x and then we put n on top. Right, so this is not an implication, it's not a logical implication, but this symbol here means that xn converges to x as n goes to infinity. Okay, so if xn converges to 0, we write this as this. Sometimes in handbooks, and maybe I will use it here and there in the notes to make my life more convenient, you can also write down that the limit for n going to infinity of xn is equal to x. Okay, so in this case here you can say that the limit of n going to infinity of xn is equal to 0. Okay, so this here and this here, this is shorthand for writing down this entire thing here or this entire thing here. Okay, good. Now we're going to see a theorem, and we're going to prove this theorem, and the theorem is the following. So we start with the sequence xn. Okay, So it says that if xn converges to some number x, and if for all n in n xn is smaller than some number z, okay, well then we have that x is smaller than z. Okay, so this is a statement of the theorem. So in other words, we have a sequence that converges to x. Every term in the sequence is smaller than some number. Then the limit of the sequence, which is x here, should also be smaller than this number. Okay, so if I put a graphical illustration, so we have a number z that some are fixed, and we have a sequence of xn's that all live. So x1 may be here, x2 may be here, x3 may be here, x4 may be here, and so on. And they're all smaller or equal to this number here. Then it says that if this sequence settles down, so in a sense it converges to some number x, then this x should also be smaller than z, right? So the sequence cannot jump to something that's above z in limits. Okay. So this is a very handy theorem that you will use several times in this course. So this is why I would like you to know it, and we're going to prove it. Okay. So for the proof, what are we going to do? Let's try a proof by contradiction. Okay, so here we have an implication, right? If this is true, then this is true, right? So we have an implication. So you can say that P implies Q, right? So for proof by contradiction, what do? We assume the opposite, right? We assume that what's stated here is not true, and then we somehow try to get a contradiction out of this. Okay, so we first need to negate P implies Q. So the negation of P implies Q, remember, not P implies Q, is the same as P and not Q. Okay, so what do we assume? Assume that P is true, right? So xn converges to x. We assume that for all n in n, xn is smaller or equal to z, and then we assume that zq is false, so x is bigger than z. Okay, so if all these things are true, what happens? We have a number z, we have x1, x2, x3, x4, and so on. All of these live here in the area below z, right? So every element of the sequence is to the left of z. And then we have an x, which is strictly bigger than z. And in some way, this sequence converges to this x. So let's write down the full definition of convergence, right? So the full definition of convergence says that for all epsilon bigger than 0, there exists an n epsilon in natural number, such that for all n greater or equal to this n epsilon, xn minus x is smaller than epsilon. Okay, so basically what this definition says is that for any epsilon that I can take, I can go far enough into the sequence such that I'm epsilon close to x. Okay, so why would this be a problem with this definition? Well, you can see that if in the end I have to get arbitrarily close to x, then probably at some point I have to pass this red barrier, right? If I take epsilon small enough, right? So if I look at this picture that I have drawn here, right? Eventually you have to be epsilon close to x. So if I take epsilon small enough, so for example, if I take epsilon to be something like this, right? So eventually I have to be in this region, but then this would contradict with the second condition that every term is here below z, right? So this is how we are going to obtain the contradiction that we are looking for. Okay, so let me try to find a new piece of paper. Okay, so let's try to make this somewhat more formal. So what are we going to do? We know that this is true for every epsilon, so we're going to pick a particular epsilon, and then we're going to see that this gives us a contradiction. So what is going to be this epsilon? Well, this epsilon is going to have to be between z and x, right? So what can we do? For example, we can take epsilon to be equal to x minus z over 2, right? This is an example. And for this, epsilon will be halfway between z and x. You can also take x minus z over 3, over 4, whatever, as long as this epsilon distance is, epsilon below x is somewhere between z and x. Okay, so every epsilon here will work. And we know, so let us call this, let's give some numbers, right? So let's make this condition 1, and this is condition 2, and this is condition 3. So from condition 3, we know that x is strictly bigger than z. So we know that this is greater or equal to 0, right? So this is from condition 3 here. So we have an epsilon that satisfies the definition. So we know that this has to be true, right? So from condition 1, what do we know? Sorry. So we know that there exists in big N and n, such that for all n greater or equal to n, let me write this in terms of the interval, right? So x minus epsilon is smaller than xn is smaller than x plus epsilon. Okay. So for all n greater or equal to this in epsilon, let's use this value of epsilon and plug it in here. Okay. X minus z over 2 is smaller than xn is smaller than x plus x minus z over 2. So we see that the violation will occur here, right? Not here. So basically we can drop the second one, but let's see what happens when you continue with this general inequality. So for all n greater or equal to n epsilon, so let's bring this to a common denominator. So we have 2x minus x, which is x, and then we have minus z, so this is plus z over 2 is smaller than xn is smaller than, so here we have 2x plus x, so this is 3x minus z over 2. Okay, so let's take this first part here. So we have that xn, so for all n greater than n epsilon, right? So these are all implications, of course. So for all n greater than n epsilon, this is bigger than x plus z over 2. What do we also know? We know that x is bigger than z, right? This is from part 3 here. So we know that this is bigger than z plus z over 2, which is equal to z. Okay, so we have found that for all n greater or equal to n epsilon, xn is greater or equal to z, or strictly bigger than z. Okay, so let me write it out here for completeness. Xn is bigger than z. However, you also have seen that for all n, right? So in particular also for these, for all n, xn is smaller than z. Okay, so this contradicts this. So this is with 2, and you have contradiction. Okay, which means that not all these 3 things are possible, which means that P implies Q by proof by contradiction. So we have done some mediocre lifting, I would say, so maybe it's time to take a short break as a mental pause. We're going to talk about the convergence lemma. This is a lemma that's not proven in the main text of the lecture notes, as you will see. However, it is stated, and we're going to give a proof of this lemma in one of the exercise sessions. It's a bit technical, so I would like to keep it out of focus of the main arguments. What I'm going to do, however, is I'm going to state the theorem. I'm going to give you some intuition, and I'm going to show you how we can use this convergent lemma in order to demonstrate other properties of sums and differences and products of sequences and their convergence. Okay, so the convergence lemma. So what we do, we need some ingredients, and the ingredients are a sequence of sequences, right, or a number of sequences. So let me denote y1n a sequence, y2n a sequence, and so on up until y big R n in it, right? So what do we have? You have one sequence, you have another sequence, and so on until the rth sequence. So here this superscript, right, is the sequence refers to the sequence, the first sequence, the second sequence up to the rth sequence. The subscript refers to the element in the sequence. Okay, so for example, ij, this is the ith sequence and the jth element in the ith sequence. Okay, this is just to give you the notation of this. Okay, so what do we have? You have a number of sequences, and you assume that all of these sequences converge to 0. So y1n converges to 0, y2n converges to 0, and so on. Also the last one converges to 0. All these sequences converge to 0. So these are the ingredients, and then we have a sequence, let's call it xn. That's also a sequence in R. So all these are sequences in R. All the y sequences converge to 0, and then you have a sequence xn. Okay, so these are the ingredients of the convergence lemma, and now we can state the lemma. So if there exists numbers, let's say alpha 1 up to alpha r, right? So these can be real numbers, and let's exclude the number 0 for easiness, right? So we have r numbers different from 0, and you also have that there's a big number n, such that for all n greater or equal to this big N, the following is satisfied, namely that the absolute value of xn is lower or equal to some expression, and this expression is a sum from j1 to big R of alpha j y j n. Right, so this is it. So what do? You take the absolute value of yjn, which is the n sequence in the sequence j, you multiply it by some number, okay, and you add them all up, so you get another number. If this number is greater or equal to the nth element in the sequence x, what do we have? Well, if this condition is satisfied, you have that the sequence xn also converges to 0. Okay, so this is the lemma, statement of the lemma. If this property here is satisfied, then xn converges to 0. So what's the intuition behind this result? Well, we know that all the sequences sequence y1, y2 up to yr converge all to 0. So this means that this absolute value gets closer to 0 as n goes to infinity, right? And now we have a sum of terms, all of the terms go to 0, a weighted sum of terms, all of these terms goes to 0. And this is smaller, this is greater or equal to 0, but smaller than some number that goes to 0. So this number also has to go to 0. That's the intuition. So if these numbers go to 0, then the sequence converges to 0. Okay. So this is the convergence lemma. So in some sense, all of these goes to 0. The weighted sum goes to 0 because this non-negative number is less or equal to something that goes to 0. Xn also goes to 0, and you have convergence. Okay, so let's see how we can use this convergence lemma to show some useful properties of convergent sequences. So let's have a sequence xn and assume that it converges to x. Let's have a sequence yn and assume that it converges to y. So what we can do is we can make a new sequence out of xn and yn. So let's, for example, consider the sequence xn plus yn. Okay, so this is the sequence where the nth element is just the nth element of xn, the nth element of the sequence y, and you add them together. Then what happens is we can show that this converges to a certain limit, and this limit is x plus y. Okay, so let's use the convergence lemma to prove this. So basically, in terms of the convergence lemma, what we need to do is we need to establish this kind of inequality. Right, we have to write the sequence that we would like to converge to 0, less or equal to weighted sum of sequences that converges to 0. Okay, so what do we want to show that converges to 0? Well, we want xn plus yn to converge to x plus y. Okay, so if you take the absolute value of xn plus yn minus x plus y, we would like that this converges to 0. So we would like to write this as a weighted sum of sequences that converge to 0. Okay, so the idea is simple. Let's just rearrange this and rewrite this. First, what we can do is you can take xn minus x and then plus yn minus y. Okay, so we get the absolute value of xn minus x plus yn minus y. Okay, so in the next step, we use basically the triangle inequality for the absolute values. In other words, the absolute value of a sum is always lower than the sum of the absolute values. Okay, so we have that this is less or equal to xn minus x absolute value plus yn minus y absolute value. Okay, so what do we know? We know that the sequence xn converges to x. Right, this is this part here. So we know that the absolute value of the difference of xn and x converges to 0. So we have that this goes to 0. You also have that this goes to 0 because yn converges to y. So now we can use the convergence lemma, right? Because this inequality, this is xn minus x and yn minus y, both of them go to 0. We have a weighted sum. Now here the coefficients are equal to 1. Okay. And we have that this sequence is less or equal to this weighted sum, and it actually holds for every n, right? So we can take big N to be simply equal to 1. Okay, so the result of this convergence lemma then says that this sequence here converges to 0. So we have that xn plus yn minus x plus y converges to 0. So this is by the convergence lemma. And this is the same as saying that the sequence xn plus yn converges to x plus y. Okay, so the use of the convergence lemma really simplified the proof of this theorem. So let's do another one. Again, let's start from a sequence xn that converges to some number x. Start from a sequence yn that converges to some number y. And now we're going to prove that the product of xn and yn converges to the product of x and y. Okay, so if you take the product of two sequences element wise, this converges to the product of the limits. Okay, so let's again prove this, in order to show that this goes to 0, we have to look at the absolute value of the difference between this and this, when n goes to infinity. So we can look at the term xn minus xy, and you have to show that this converges to 0, right? Which is the same as saying that xn converges to xy. And again, what we're going to do is we're going to use the convergent lemma. So this here now is this, okay, and you have to show that it's smaller than a sum of sequences, all of which converge to 0. Okay, so we know that these sequences converge to 0, okay, and here we have a product. So how can you write this in terms of xn minus x and yn minus y? Okay, so here's the trick. What we can do is we can write this as xn minus y. Sorry. Let's redo the trick. We can write this as xn minus xy, and now we're going to add and subtract the same term, and the term is minus xny and plus xny. Okay, so we will do this many times in this course. We're going to add 0 to something, and if you add 0 to something, then nothing changes, but the 0 is of a special kind. Okay, so here we subtract and add the same thing, so this is 0, it doesn't matter, I can add 0 here, nothing changes, but doing it in this way will be quite helpful. Why is this? Well, you can take this together, the xn's, and you can also take the y's together. Okay, so let's see what happens if we do this. Well, then this is equal to xn yn minus y, okay, plus y xn minus x absolute value. Okay, just this is rewriting this sum. You have a sum, you have the absolute value of a sum, so we know that this is less or equal to the sum of the absolute values plus y xn minus x. Okay, now we have an absolute value of a product, and you should know that the absolute value of a product is equal to the product of the absolute values. Okay, so I take xn and then times the absolute value of yn minus y plus y and then the absolute value of xn minus x. Okay, so here we have something that goes to 0, yn minus y. Here we have something that goes to 0, xn minus x. So we are quite close to this kind of form. We have sequences that go to 0 and then we multiply it by a coefficient. Okay, so for the second term, if you notice that absolute value of y is just a fixed number, right? So y is a number, no problem here. So we can say, okay, this is the parameter alpha that you were looking here. Here, this is a bit more of a problem because xn varies, right? So this is not a fixed parameter. This is not a fixed alpha, but this varies over time. So we cannot immediately apply the convergence lemma to this expression here. So we need an intermediate step. So what's the intermediate step? So the intermediate step uses the fact that xn converges to x. Okay, so we know that xn converges to x. So we know that for all epsilon bigger than 0, there exists an epsilon in n, such that for all n greater or equal to an epsilon, let me put it like x minus epsilon is smaller than x is smaller than x plus epsilon. Okay. So what will we do? We'll just fix an epsilon. For example, set epsilon equal to 1. Okay, I could have taken another number, but let me take 1. So we know that this holds, so we know that there exists a number n1, right, such that for all n greater or equal to n1, x minus 1 is smaller than xn, this should be xn, sorry, is smaller than x plus 1. Okay, so what we're going to do, we're going to take this expression and only look for numbers above this number n1. Okay, so for all n greater or equal to n1, let's take this expression here, xn yn minus y plus y xn minus x. Okay, and because n is greater than n1, we know that xn is bigger than x minus 1. Xn is smaller than x plus 1. Okay, so in absolute value, x is smaller than the absolute value of x plus 1, right? Because xn is sandwiched between x minus 1 and x plus 1, the absolute value of x is no more than 1 away from the absolute value of x. Okay, so for all n bigger than this n1, we have that this is smaller than the absolute value of x plus 1 times yn minus y plus y xn minus x. Okay, what we did here is we used the fact that xn is smaller than x plus 1 if we restrict ourselves to these numbers, and then we have less or equal sign. This is non-negative, but it can be 0. In case this is 0, we have an equal sign. Okay, but at least we have a less than or equal sign. Right, so then this can be written as the absolute value of x times yn minus y plus yn minus y plus the absolute value of y times xn minus x. And now we are ready to use the convergence lemma, right? So we need to have a weighted sum of sequences that converge to 0. So what do we have? We have that this sequence converges to 0, yn minus y. Again, yn minus y converges to 0, xn minus x converges to 0. Here we have a fixed coefficient, which is the absolute value of a number. Here we have a fixed coefficient of 1. Here we have a coefficient equal to y. So, and this holds for any n bigger than this n1, right? So we conclude that this also converges to 0. So xn yn minus xy, this thing converges to 0, and this is by the convergence lemma that we have seen. So xn yn converges to xy. So let's continue with the following case. So consider a sequence xn converging to x and assume a number alpha in R. We would like to show that this implies that the sequence alpha xn, right, so this multiplies every term in the sequence x by alpha, that this converges to the number alpha times x. Okay, so if you multiply every element of the sequence, and if the sequence converges, then the limit will be multiplied by the same number. And again, we're going to use the convergence lemma. So in order to show this, we would like to show that alpha xn minus alpha x, that this sequence here, this converges to 0. Okay, so what we can do is we can take the alphas together. So we have the absolute value of alpha xn minus x. And now we have the absolute value of a product. So we can write this as the absolute value of alpha times the absolute value of xn minus x. And you can use the convergence lemma, right? So what do we need? We need a sequence equal to the weighted sum of the number of sequences that converges to 0. So here we have a sequence that converges to 0 multiplied by some number, and an equal sign is also a less than equal sign, so this is okay. We can use the convergence lemma to show that alpha xn minus alpha x converges to 0. By the convergence lemma. So alpha xn this sequence converges to alpha x. So this one was quite easy. The following one is a bit more tricky. So let's do this, the last exercise. So we have a sequence xn converging to x, we have a sequence yn converging to y, and here we assume that y is different from 0, and it will become obvious why we require this. And now, given this, we would like to look at the sequence xn over yn. Okay, and you would like to show that this converges to, not so unexpected, the ratio of x over y. So y has to be different from 0, otherwise you cannot divide x by y. Okay, division by 0 is not well defined. Okay. So again, we're going to use the convergent lemma. So basically, in order to show this, we would like to show that the ratio of xn over yn minus x over y, that this sequence here converges to 0. So first thing that we can do in order to get this in terms of xn minus x and yn minus y, right? These are the sequences that we know converge. First thing that we can do is we can put this on a common denominator, right? In this case, we have that in the numerator we get xny minus xyn, and you divide this by y. Okay. So we have the absolute value of a quotient. So this is the quotient of the absolute values. So we can take the absolute value of the numerator minus xyn and then divided by the absolute value of yn y. Okay, here you have xny minus xyn. So we're going to use the same thing that we did for the product. So we're going to add and subtract the same term, and here we're going to subtract the term xy and we're going to add the term xy, and then we are left with minus xyn. In the denominator we have the absolute value of a product, so this is the product of the absolute values, so we have yn times the absolute value of y. Okay, here we're going to take the y's together, and here we're going to take the x's together. So this gives us the absolute value of yxn minus x plus x y minus n, and this is divided by absolute value of yn times the absolute value of y. Okay, so here we have the absolute value of a sum. We can use the triangle inequality, so this is less or equal to absolute value of y times xn minus x plus the absolute value of x times y minus yn, and then the absolute value of yn times the absolute value of y. Okay, and now again you have a product, the absolute value of a product, so this is the product of the absolute values. So we can write this as y and then divided by yn y, and then we can do it by xn minus x plus the absolute value of x divided by the absolute value of yn times the absolute value of y, and then y minus yn. Okay, so we see we're getting closer and closer to this kind of expression where here we have sequences that converge to 0 and we multiply them by some number. Okay, so here we have a sequence that goes to 0 because xn goes to x, yn goes to y, so this sequence also goes to 0. And here we have something that looks like a number, and here we have something that looks like a number. The only problem is that here, so actually we can divide these two, so that's not a problem. The only problem that is a problem is that this yn is not a fixed number, right? It varies over n. So we would like to make sure that this is less or equal to xn minus x, and here yn minus y, which is the same as y minus yn, and here a fixed number and here a fixed number. Okay, so in order to get this inequality going on, we have to show that yn, at least from some n onwards, is now not less or equal to some number, but bigger, greater or equal to some number. Okay. So before we continue the proof, let us make a small lemma, right? A small intermediate result that we will find quite useful. So the result says the following. So if you have two numbers a and b, and a minus b is smaller than some number epsilon, okay, so this here is equivalent to b minus epsilon being smaller than a being smaller than b plus epsilon. Okay, a is in the interval epsilon around b. Then this implies the following, namely that the absolute value of b minus epsilon is smaller than the absolute value of a, and this is smaller than the absolute value of b plus epsilon. Okay, so if you immediately see that this implies this, then you can scroll or fast forward through this proof. Otherwise, just follow along the steps that I will explain to you here. Okay, so the proof is quite easy, but it takes a few cases. So we're going to distinguish cases where, so a and b are in R. So we're going to distinguish when a and b are positive versus where they're negative. Okay, so we have four possible cases. In case 1, a is positive and b is positive. Okay, so in this case we know that a is equal to the absolute value of a and b is equal to the absolute value of b. Okay, so in this case here this inequality is the same as b minus epsilon smaller than a is smaller than b plus epsilon, which is exactly what we want. Okay, so the first case is very easy. You can just substitute the values with the absolute values. Okay, so let's take the second case. In the second case we can take a bigger than 0 and b negative. Okay, so in this case we know that a is equal to the absolute value of a, and we know that minus b is equal to the absolute value of b. Okay, we have to flip the sign of b in order to get the absolute value. Okay, so here if we switch a and b here, so if we bring b plus epsilon to the other side and a to the other side, we get minus b minus epsilon smaller than minus a. Okay, and if you take this part of the inequality, bring b minus epsilon to the other side and a to the other side, we get that minus a is smaller than minus b plus epsilon. Okay, so we will also need this expression here too. Okay, so absolute value of b minus epsilon, in this case we know that b minus epsilon is equal to minus b minus epsilon. Okay, and we know that minus b minus epsilon is smaller than minus a. Okay, and we know that a is greater or equal to 0, so minus a is smaller or equal to a, and we know that this is equal to the absolute value of a. So we have shown that the absolute value of b minus epsilon is smaller or equal to the is smaller than the absolute value of a, which is this first part here. Okay, so that's good. Then for the second part we use this. We know that the absolute value of a is equal to a because a is non-negative, and we know that this is smaller or equal to b plus epsilon, and we know that b is negative, so we know that b is smaller than the absolute value of b plus epsilon. Okay, so this b minus epsilon is smaller than the absolute value of a, and we have that a is smaller than the absolute value of b plus epsilon. So we have what we wanted to show, this thing here. So that's case 2. In case 3, a is negative and b is greater or equal to 0. So we have that minus a is equal to the absolute value of a, and b is equal to the absolute value of b. Okay, so let's start. You have that b minus epsilon is equal to b minus epsilon. Minus epsilon. right? This is the second one. And now we know that b minus epsilon is smaller than a. Smaller than a is negative, so a is smaller than the absolute value of a. So we know that the absolute value of b minus epsilon is smaller than the absolute value of a, which is this first part that we have here. Okay. And now for the second part, we have that a is equal to minus a, which is set here. You know that minus then minus b plus epsilon. Minus b is negative, right? Is less or equal to 0, so I know that this is smaller or equal to b plus epsilon, and b is equal to the absolute value of b plus epsilon. So we have that the absolute value of a is smaller than the absolute value of b plus epsilon. So this is case number 3. And then for the last instance, we take the case where a is smaller than 0 and b is smaller than 0. So in this case, you have that minus a is equal to the absolute value of a, minus b is equal to the absolute value of b. Okay. So in this case, b minus epsilon is equal to minus b minus epsilon. Minus b minus epsilon is smaller than minus a, which is equal to the absolute value of a. All right. And you know that minus a is smaller than minus b plus epsilon. Minus b plus epsilon, and we know that minus b is equal to the absolute value of epsilon, so this is b plus epsilon. Okay, so we have that b minus epsilon is smaller than the absolute value of a, is smaller than the absolute value of b plus epsilon. So this is case number 4. For every case we have shown that this is true, so this result holds. So now we can continue with the proof of the ratio. Let me try to find my papers again. So what we had is we were ending at this expression. So we had xn minus x, this converges to 0. This converges to 0, but this coefficient and this coefficient is still dependent on n. Right, so in order to show that this is less or equal to some coefficient, we have to show that the absolute value of yn is greater or equal to some number, right? Because it's in the denominator. So we're going to use the definition that yn converges to y, right? So we have that for all epsilon greater or equal to 0, there exists an n epsilon in n, such that for all n greater or equal to this big N, yn minus y is smaller than epsilon. And because of the implication that we had here, we know that this implies that for all epsilon bigger than 0 there exists an n epsilon in big N, such that for all n greater or equal to n epsilon, y minus epsilon is smaller than the absolute value of y, is smaller yn, is smaller than the absolute value of y plus epsilon. Okay, so this follows simply because this inequality here implies this inequality here. So here this inequality implies this inequality, so we also have this application. Okay, so what we're going to do is we're going to pick one particular value of epsilon. So this particular value of epsilon, let's say that we're going to pick y over absolute value of y over 2. So in here, for this we use the fact, remember, that y is different from 0. So if y is different from 0, the absolute value is strictly positive. So this is strictly positive. Okay, so we know that there exists an n, let's call it, I don't know, n2, and n, such that for all n greater or equal to this n2, now we can plug in the epsilon in here. So absolute value of y minus absolute value of y over 2, this gives you absolute value of y over 2, and this is smaller than yn, and this is smaller than 3 over 2 of y. Okay, so basically we only need this inequality here. So what do we have? We have that for all n greater or equal to n2, yn is greater than y over 2. So 1 over yn is smaller than 2 over y. Okay, and we can use this inequality here to get here. So this is less or equal to 1 over yn is smaller than 2 over y. So this is less or equal to 2 over y. Alright, so here we repeat x, we repeat y, and then 1 over yn is smaller or equal to 2 over y. Okay, you see, this is just by substituting here, and this holds, this inequality holds for all n greater or equal to this n2. Okay, and here the n2, if you see, the n2 is the one that satisfies this condition. Okay, so we're almost there. So here we have a sequence that converges to 0. Here we have a sequence that converges to 0. This is a fixed coefficient. Okay, and this is also a fixed coefficient. So we can use a convergence lemma. Right, because this will be smaller or equal to this as long as small n is greater than some number n2. Okay, so from the convergence lemma we find that xn over yn minus x over y, that this converges to 0, and equivalently this is the same as saying that xn over yn converges to x over y. Okay, so this finishes the proof of the quotient.